Yesterday in class, we talked about solving systems of equations by graphing. Here's just a quick tutorial on how to graph these two lines. Remember that you start at the y-intercept, or the b value of y equals mx plus b. Here we have a negative 3 over 1 slope, so I can move down 3 to the right 1, down 3 to the right 1. I have made a video before on graphing lines, so if you need to go watch that real quick, go watch it. For this second equation, I'm going to plot this first point at negative 2 because that's my b value, and then I'll use this positive 3 over 1 slope to go up 3 to the right 1. So notice how my two lines intersect at a point. That point is called the point of intersection. With these two lines, we can see the point of intersection very easily, but that won't happen with every line. We saw that yesterday in our live lesson, and I'll refer back to those graphs today. Since my two lines intersect at the point 1, 1, that is my solution. We're going to look at this same example, but we're going to solve this in a different way. Again, my answer here should be 1, 1. That is the point where these two lines intersect. But because graphing is not always the best method, we're going to try this with substitution. Substitution means plug one equation into the other for a variable. We need to analyze both equations and make sure that at least one of the variables is isolated. Here we see that we have two equations where y is isolated in both equations. So we're going to take one of them and we're going to substitute an entire equation into the other for a variable. So it doesn't matter which one here, but I'm just going to choose that second equation, and I'm going to put a little box around what the equation looks like, 3x minus 2. I'm going to substitute that 3x minus 2 in for y, because that's what y is equal to. So instead of writing y equals, I'm writing 3x minus 2 equals, and then the rest of the equation that I see. Now I only have an equation to solve for one variable. I can solve for x here. This skill to solve for x is a prerequisite. You did this in Algebra 1 and you did this in the very beginning of Algebra 2. So notice how I'm moving my x value to the left side, trying to keep those x's positive. I'm also going to isolate my variable x here, and I will end up getting 1 for x. Now that I have a value for x, I'm going to go ahead and use that variable that I found to substitute into one of my original equations. Remember that our solution to a system of equations is a point of intersection. So far we've found an x value, but we need to find the y value. So when I look at these two equations, I can use either one of them, but I'm going to use the one that has less stuff going on. So I'm using 3x minus 2 because there are no negatives there. Notice how I'm substituting the x that I got into that equation, and when I get my solution or my point of intersection, I'm writing that as an x comma y. I'm going to make sure that one of those variables is isolated. Now, this top equation looks the easiest for me to isolate a variable because all I need to do is add that y to both sides, and that will leave me with x isolated. It doesn't matter that my y is not isolated, it just has to be one of those variables that's by itself. So I'm going to substitute that entire equation into the other. I'm going to rewrite that 7x minus 7y, but instead of writing x, I'm going to put a set of parentheses because I'm going to substitute what x is equal to into that set of parentheses. So here I'll plug that 3 plus y into the equation. I'm substituting that expression into the other equation. And then I just simplify. So 7 times 3 is 21, and 7 times y is 7y. I should also notice that 7y minus 7y adds up to 0. So all I'm left with is 21 equals negative 3, which is not true, which gives me no solution. That makes sense because when we graphed these yesterday, we did notice that they were parallel, which means they will never intersect. Go ahead and try this one on your own. Pause the video, substitute an equation into the other, solve for both x and y, and come back when you're finished. So you'll see here that I took that x minus 3 and substituted it in for y. So instead of y equals, I have x minus 3 equals, and then the rest of the equation, 4x minus 9. When I solved this, I got 2 for x, and then I used the easier looking equation. So I used x minus 3 to plug in that x value that I found. Then I found y, and I found that point of intersection, which matches the same point of intersection that we graphed yesterday. I could have also used the other equation here. 4 times 2 would be 8, and then 8 minus 9 would still give me -1. So I could have used that other equation as well. I just like to use the ones that look the easiest. Yesterday, we found out the hard way that graphing is not the best method to solve this system of equations. We couldn't quite see the point of intersection. We had a lot of decimals going on. So today, we're going to solve this using substitution. Notice how I have y equals 5. So I already know that my point of intersection is going to have a y value of 5. I'm just going to plug that y value of 5 into my other equation. So instead of 6x plus 8y, I'll have 6x plus 8 times my y value of 5, and then equals -22. So from here, I'm just going to solve. You should start to notice that we're going to get a fraction for our answer. -62/6 can be simplified. We definitely don't want to write that as a mixed number because mixed numbers are dead, but we can simplify that by dividing both numerator and denominator by 2, which leaves us with -31/3. We definitely wouldn't be able to predict that x value if we were graphing this by hand. I'm doing this voiceover in the library, and I think everybody's thoroughly annoyed with me by now, so gotta go. See you next time.